So I just wanted to make a quick video about finding the zeros of a polynomial function. Now, everything we do in chapter 3 pretty much leads up to being able to do this one thing. So these are the notes packets that we use in a face-to-face class. So I just wanted to, for this particular midterm exam, kind of run through how to do this and how to use a calculator and how this all works. So it says here, our definition of a polynomial, a sub n, this little guy right here, a sub n is called the lead coefficient. And this little guy right here on the end, a sub 0, is the constant. So if the polynomial has any rational zeros, you could find them in the form of p over q, where p is actually a factor of a sub 0, and q is a factor of a sub n. So what you basically want to do is you're going to write the factors of a naught, or p, over all the factors of q. So again, to summarize, this is again just the notes we do in class. To summarize, p is a factor of a sub 0, and q is a factor of a sub n, the lead coefficient. So the rational zeros test actually gives us a list of possible zeros. You know, it may or may not, all of them work, none of them may work. It is possible to have multiplicity with some of your zeros, but it'll at least give us a list of possibles. Now, I'm going to go ahead and show you how to find the list of possibles, but this is not really how we work these problems, and I'm going to get to that in just a second. To find the possible rational zeros, again, we're going to use this little guy over here. The 16 is going to be p, and then the a sub n, the coefficient of the x to the third, is going to be q. Now, you've got to be able to do this correctly, and I know in my math lab when you're doing your homework, it kind of leads you to type this out correctly, but when you're doing this by hand, here's kind of what you want. P over q is going to equal plus or minus all the factors of 16 over the factors of 1, which is just 1 times 1, which is 1. We really like to see that lead coefficient be a 1, just because I don't have any factors of 1 other than just 1. So now we're going to list out the possibles for 16. That'll be 1, 2, 4, 8, and 16. And then, of course, what you're going to do is you're going to say, all right, the possible p over q's are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16. Now, this gets far, far more complicated when your a sub n is something other than a 1. And that's kind of why we have this second example, is to sort of show that. All right, so we know that we want p over q to be plus or minus all the factors of 12. Again, here's your p, and 4 this time is our q. So all of the factors of 12, which is going to be a lot, 1, 2, 3, 4, 6, and 12, and then all the possibles of 4 are going to be 1, 2, and 4. Now, I'm just going to tell you, you cannot leave your answer like this. This is totally 100% unacceptable. So what we have to do is we have to have some sort of a systematic way to take all these numerator factors and write them over the denominator factors. This is kind of how I do it. Just do it one at a time. So my possible p over q's are, and I'm going to put a big plus or minus, and I'm going to use a parenthesis. That way I don't have to do it like I did above. So the first thing I'm going to do, if it's p over q, is I'm going to take 1, and I'm going to put it, 1 over 1 is 1, 1 over 2 is 1/2, 1 over 4 is 1/4. I'm finished with the 1 in the numerator, and I'm going to move over to the 2. So I'm going to go 2 over 1 is 2, 2 over 2 is 1. 1 is already in the list, so I'm going to skip that. And then 2 over 4 is 1/2. That is also already in the list. I'm going to skip that. Now I'm going to go over to the 3. 3 over 1 is 3. 3 over 2 is 3/2. And 3 over 4 is 3/4. Common. Now we'll move over to the 4. 4 over 1 is 4. 4 over 2 is 2, which is already in the list, so I'll skip that. 4 over 4 is 1. It's already in the list. I'll skip that. And now I can move over to the 6. 6 over 1 is 6. 6 over 2 is 3. 3 is already in the list, so I'll skip that. 6 over 4 actually reduces down to 3/2. It's already in the list, so I'm good with that. Now I'll go to 12. 12 over 1 is 12. 12 over 2 is 6. It's already in the list. 12 over 4 is 3. It's already in the list. Close my parentheses, and there's my list of possible zeros. Now, this is called the fundamental theorem of algebra. It's a great theorem. It's something that any mathematician would want to spend an enormous amount of time on. What the fundamental theorem of algebra does is it just tells us that these zeros exist, and it's sometimes called the existence theorem. Every polynomial function of a degree n, where n is greater than or equal to 1, any function that has a degree bigger than 1, with complex coefficients, remember real numbers are set in the set of complex numbers, has at least 1 zero in the system of complex numbers. And this is indeed called the existence theorem because it tells you that a zero exists. Doesn't explain how to find them, doesn't help you at all in that regard, but it does tell you that one exists. So here's kind of what we're going to do is we're going to go to the next page and we're going to look at how do we find them. And you know, I'm pretty old school, so I apologize about that. But when we used to do these, I had to walk to class uphill through the snow both ways, and so we had to do all of this work by hand. All right, so the way we used to have to do it back in the old days is we would be given, this is all we're given. We didn't have graphing calculators. Graphing calculators didn't come out until 1995 or 96. And I graduated from college in 1986, 10 years prior. So I didn't have any kind of technology that would help me with this. So what we would do is we would list the P over Qs. Then we would start using synthetic division and we would start trying all the different P over Q numbers with synthetic division until we got a remainder 0, so we knew we had an answer. But what we do today is we use a graphing calculator. And what we're going to do is we're going to come over here and we're going to type it in. So we're going to type in x to the third, x raised to the third, arrow over, plus 2x squared minus 5x minus 6. Now I'm probably going to change my window from -5 to 5. And make my y-axis also -5 to 5. This is just to zoom in a little bit on the graph to see kind of what we're looking at. Now, on this particular screen, this particular polynomial that I actually cannot factor by grouping, you can kind of see, there are a couple of ways to tell. You can tell that we're going through the axis at -1, -3, and at 2. Another way to look at that is use the second key. If I use a second key and come over here to table, I can see my zeros very, very clearly. At -3, y equals 0. At -1, I get a 0. There's my y-intercept at 0, -6. And I have another 0 at 2. So let's just use the 2. So if we say x equals 2, what would that look like? Well, I would do 2, and then I would come down here, I'd put 1, and then 2, and then -5, and -6. Drop down your 1 to kick off your synthetic division. 2 times 1 is 2, 2 plus 2 is 4, 2 fours is 8, 8 and -5 is 3, 2 threes is 6. Sure enough, just like it showed on here, +2 is in fact a 0. Now, This is what we would have done trial and error with the P over Q's by hand. What I can do now, well, what is this stuff left over? Well, this stuff left over happens to be x squared plus 4x plus 3 equals 0. You know what? According to this, -1 and -3 are also zeros of this particular polynomial. So guess what I'm going to do now? This guy factors. Are there factors of 3 that add up to give me 4? In fact, in this instance, there are. So I'll say x plus 3, x plus 4. So now I know x equals 2, x equal -3, and x equal -1. There I found the zeros. Now, I'm going to concede this particular example is extremely easy. All of your zeros are in really integers on the x-axis. Very simple. This is not the kind of problem you're going to see on a test. Sorry, that's just how it goes. All right, so this guy right here. Here's how I would normally work a problem. I still, again, old school, look at the P over Q's. I'm thinking about all the factors of 52. So I might want to go second quit. I'm going to go 52 divided by 2. Okay, 26. So my factors of 52 are probably going to be 1, 2, 4, and I believe 13 and 52. And all of those would be over 1. So these are my P over Q's. Now I'm going to come over here and I'm going to plot this. I'm going to clear this guy out. X to the third minus 2x squared minus 11x plus 52. I'm going to go ahead and graph it. I'm going to see if I get a hit here. Wait for it. Okay, it's done. So you might say, well, I need to make my axis. Well, no, you don't need to make your axis bigger. If you've got a hit right there, you're gold. This is a third degree polynomial. The degree is 3. If you have found one, just one, you can find the other 2 using the quadratic formula or factoring, and we're home free. I'm looking at this and I'm thinking, that guy's going through -4 right there. Shall I double check? Second and table. Sure enough, right here at -4, I've got a 0. So what I'm going to do is I'm using the calculator now. Instead of trying all these P over Q's and trial and error with synthetic division, I'm going straight for the graph and I'm going straight for -4. That's my guy. Forget about the list. Don't care. -4. And I'm going to do my synthetic division. Now, why do I have to do this? Well, because the reason I have to do this is because if I know negative, I don't know the other 2. Where are the other 2? They may or may not be on the x-axis. They may be complex. 1 real, 2 complex roots. How do I find them? The only way that I can get this work down from a third degree polynomial to a second degree polynomial, get this down to a quadratic work, use a quadratic form or whatever I have to do, is to do the synthetic division with the 1 0 that is absolutely true. And that's why I'm using -4 and using synthetic division so I can go that route. Okay, so I'm going to drop down the 1. -4 times 1 is -4. Add those together, -6. I'm going to get 24. Yes, the numbers are getting pretty big. That is going to give me 13. And if I am not mistaken, 4 times 13 is 52. So -4 times 13 is -52. Sure enough, there's my 0. Now, how do I find the rest of the zeros? Well, I've got a quadratic here. Does it not say x squared minus 6x plus 13 equals 0? Guess what? Not going to factor, is it? 13, are there any factors of 13 that add up to give you 6? No, 13's prime, just 1 and 13. So here's what I'm going to have to do. X equals -b, so -6, so 6 plus or minus the square root of b squared, -6, don't forget your parentheses, minus 4 times a times c, all over 2a. Now all I've got to do is I've got to clean this guy up. So this is going to be x equals 6 plus or minus the square root of 36. And remember, This is 52, so 36 minus 52 all over 2. All right, so x equals 6 plus or minus the square root. 36 minus 52 happens to be negative 16 all over 2. The square root of negative 16 happens to be 4i. So I will come over here and say x equals 6 plus or minus 4i all over 2. The reason that we did in chapter 1, we reviewed this, is that you could break this up correctly. Please simplify this correctly. The correct way to do this is 6 over 2 plus or minus 4i over 2. Therefore, we're going to get 6 over 2 is 3 plus or minus 2i. So now what we're supposed to do is we're supposed to find all the zeros. So x equals negative 4 and 3 plus or minus 2i. And that is how this is done with a calculator. You've got to use the graph to find the first zero. Once you find it, use your synthetic division to create this quadratic. Use a quadratic formula. Find all your roots. And we're going to stop the video right there, and I sure hope this helps.